to ये
Hi everyone, welcome to today's session on linear algebra through geometry. Let's wait for a few more minutes so that everyone can join and then we'll start the session. So, hi everyone. Let's start the session. I hope I'm audible and my screen is visible. Please confirm by typing in the chat box. Okay, great. So in this week, what we have seen is you must have gone through the video lectures sent by the NPTEL team. So till now, what we were doing, we were only considering 2D, two-dimensional space, and we were solving, looking at some linear algebra problems on those two-dimensional vectors, right? So in this week, you were introduced to the next higher dimension, that is three-dimensional vectors. Then what are the arithmetic operators on those vectors? Then what is the idea of linear dependence and independence on of these vectors and the linear combination of the vectors? Fine. Again, we extended the formulation for dot product from 2D to 3D and the definition of orthogonality in 3D space. Then you must have seen a projection of three dimensional vector in the 3D space. Then what is a plane and how to represent a plane in a three-dimensional space. So basically, yeah, how to represent a 2D plane in a three-dimensional space. Then from the equation of plane, can we find the shortest distance of a point from the plane? And lastly, we saw how to find the volume of a parallel pipe formed by three vectors, right? That is essentially the scalar triple product. So these were the concepts that were covered in this week, right? So it's a very brief introduction, right? So what are 3D vectors? So till now we were only considering the XY plane, the two-dimensional Cartesian plane, and the vectors defined in this space as the 2D vectors. Now, since we are dealing with 3D vectors, we have another basis, that is the Z-axis, and we can define vectors in this space. So for example, this is a vector in 3D space, right? This is a vector in 3D space. This is a vector in 3D. This is a 3D space vector, right? So now the in 2D we were representing vectors as, let's say, 1 comma 1. In 3D the vectors will be represented with three coefficients for each of the three bases. So 1 comma 1 comma 0 will be the 3D vector for three-dimensional representation of this vector in the 3D space, right? Now again, it gives us a new basis where we can extend our space. So there are more vectors that can be represented using this kind of representation. For example, 1 comma 1 comma 1, 1 comma 2 comma 0, 1 comma 2 comma 3, something like that. So this 1 comma 2 comma 0 existed in the xy plane also, but now we can also represent vectors like 1 comma 1 comma 1, 1 comma 2 comma 3 in the 3D space if we consider the all three basis functions, right? Then what are the arithmetic operations? You must have seen what is addition, right? It is the same as doing addition in the 2D space. Then subtraction, right? Subtraction, this is also same. Subtraction. Then scalar multiplication, same thing, right? Scaling the vector, scalar multiplication. Then you must have seen vector products, right? Sorry, vector products. There are two type of vector products that you must be introduced by now. One is the dot product, right? Then there is the cross product of the vectors. So dot product results in a scalar. So dot product is essentially a mapping from R3 cross R3 to a scalar, right? And the cross product is a mapping from R3 cross R3 to R3, right? Then linear combination of vectors. So these were basic arithmetic operations that you must have seen. And then linear, what is the meaning of linear combination and linear independence, right? Linear combination. So essentially, if you have two vectors, let's say v1, v, u, and v, right? Let's say you have vector u and v, both belong to R3 space, and we have some scalars c1 and then c2, which belong to R1 space. These are basically scalars. Then you can write a linear combination. So let's say z is a vector that belongs to R3 space, and z can be written as a linear combination of c1 u1 plus c2 v, c1 u plus c2 v, right? C1U plus C2V, right? Now this represents that is essentially a linear combination of these two vectors, right? If C1 plus C2 equals to 1, this is also known as convex combination. Right? So these were some basics that you must have seen in the lectures. Fine. So now, yeah. Then what is the meaning of linear independence and dependence? This again you must have seen linear dependence, right? A vector is said to be linearly dependent. A vector, let's say U, is said to be linearly dependent to the vector V if we can say U is some scaled version of V, right? K into V, where K is a scalar here, right? K is a scalar here. So this is the idea of linear dependence, right? And similarly, you can say if you can't say that U is not equals to K into V, basically U is equals to some C1V plus at least one non-zero vector and non-zero scalar C2U v plus w, then u is linearly u and v are then u and v are linearly independent, right? Fine. So this is the idea of linear combination and linear independence. Then dot product is well familiar to you all. We have seen this, and orthogonality essentially means perpendicular vectors, right? Orthogonality essentially means perpendicular vectors. It essentially means u and v are orthogonal if u dot v is equals to 0, right? This essentially means, let's say this is a vector u and this is a vector v. So they form an angle of 90-degree between them, right? So this is the definition of orthogonal vectors. And you all know u dot v can be computed by the formulation norm of u, magnitude of u into magnitude of v into cosine of the angle between them. And now angle is theta here. Theta is 90-degree here, right? Or cos 90 is 0. So this becomes 0 for perpendicular vectors, right? Then projection of vectors. Projection we have already seen, right? So now how to what are planes, right? How to represent planes. So till now what I have done is I have simply used the definitions from the 2D Cartesian space and extended to a 3D space of vectors, right? I took the definition from a 2D space of vectors and then extended it to 3D space, and I just rewrote all the definitions again. So these are all basics. Now let's go into new things that we are seeing. So if you are considering only 2D vectors, you had only one plane, right? But if you are considering the 3D space, you can have multiple two-dimensional planes. For example, so, so let's say this is our right. So let's say hmm, so this is the positive z-axis. This is the positive x-axis, and this is the positive y-axis, right? So you can always draw infinite number of planes in this three-dimensional space, right? Right. So in this three-dimensional space, you can draw this is a plane, then this is also a plane, this is also a plane, right? You can draw infinite number of two-dimensional planes in this space, right? Let's take a basic example of XY plane, right? XY plane. It essentially what it looks like. The normal to this plane is let's get back, right? First, let's start with XY plane. So XY plane, any vector in the XY plane can be represented as the values x comma y comma 0, right? Any vector in the XY plane can be written like this, right? Or you can always say ax plus by is equals to c. So this is the equation of a plane in the equation of a line in the XY plane, right? Okay, fine. So this is how you represent the plane. So for representing plane, you must have seen the that we use the definition of a normal. So what is the normal? Normal is essentially a unit vector perpendicular to a plane, right? So you can so how to represent plane, how to parameterize a plane. So let's say this is a two-dimensional plane in the 3D space, right? So let's say this is a two-dimensional plane in a 3D space. Then for sure there will be a single, there will be two vectors, two directions that are perpendicular to this plane, right? One is this direction that is essentially coming out. So let me show you like this. This is not a good representation here. Huh. So let me show you like this. So let's say we are again in the Cartesian plane, right? We are again in the Cartesian space. This is the XY plane, right? X and Y. Right. Now, this is also a plane, right? This is also a plane in the three-dimensional space. So there must have been a z-axis here, right? There is a z-axis coming out like this, which is essentially perpendicular to both x as well as y. So, right, this is perpendicular to the xy plane. Now, what is the direction of normal for this plane? There can be two vectors with two directions which are essentially pointing in perpendicular, which are orthogonal to this plane. So one can be coming out like this, right? One can be going in like this, right? So these are the two probable directions for any vector that essentially will be orthogonal to this plane, right? And again, you can check this. So let's say we are representing the xy plane. So any vector will be represented as some x value, some y value, and some. So let me write this like this: some x c coefficient c1, cx, some coefficient cy, and then zero in the z-axis because we are only representing the xy plane. Now I'm saying there are two possible directions. One direction is, so let's say we call it normal one. A unit vector in that direction can be represented as 0, 0, 1. This is the one direction in positive z. And then another direction is n1. Let's negate this and you will get 0, 0, minus 1, right? Now you can check, you can take the dot product, right? So this is any vector. This is any vector in the space in the 2D plane, right? So now you can always check v dot n1 equals to 0 and v dot minus n1 basically is equals to 0. So now which vector should we choose as our normal? It depends upon the user, right? So for us, for our course, let's consider positive z. So this n1 as the normal. So the vector unit vector coming out of the plane, let's consider that vector as our desired normal. This is the normal for this 2D plane, right? So this is the z direction, positive z direction. So now what you need to represent a plane? You need a normal vector, right? But you need one more information. For example, let's say this is a plane that looks like this and that goes through the zero, that has a normal plus 0, 0, 1, right? But again, I can also I can also um, draw a plane, right? Um, yeah, I can also draw a plane like this. So let's take this plane. Um, Let me draw it again. So now this was the XY plane, and let's shift the plane that we are trying to get to by one length in the z direction, right? So let's take a new plane that essentially sits on z equals to 1. So this will be the plane, right, that hits the z axis at, so right. So this is essentially hitting the z axis at some point, let's say here, right? So this is hitting at this point, and this is essentially, let's say, z equals to 1. Fine. So this is a new plane. Again, the what can be the normal for this plane? The normal can be 0, 0, 1, right? But again, both these plane, this was the xy plane and this was the xy shifted plane, right? Again, these both planes have a normal, which is 0, 0, 1. So both the normals are same. So this tells us that, so basically this also has a normal that is along in this direction, right? So the direction of both normals are same. So this says that we cannot have only one information to represent a plane. We need at least two informations, right? So then another information can be, for this plane, we can say the plane passes through the point 0, 0, 0. It passes through the origin, right? For this plane, we can say it passes through 0, 0, 1. Now, using these two informations, we can always say that this is a different plane than this plane, right? So basically, these are the two informations that we need to represent the plane. Fine. Now, since now we are introduced to planes, we can have multiple things that we want. The first question arises is, ah, so the first question arises, let's say we have a plane that looks like this. So this is a plane and we have a vector v that is here, right? So now what is the shortest distance of this vector v from this plane P, right? So this is the plane, let's say. So this is a two-dimensional plane here, and we want to find the shortest distance of v from this plane. So how to find that shortest distance? So that shortest distance will be covered by a vector originating from point V to some point on vector point P, on the plane P. Let's call this point as Q, right? Such that Q minus V, Q minus V, this is a vector, right? So now this dot any vector in this plane. So let's draw any other vector in this plane, right? So let's say this is a point that lies in the planes represented by the vector x. So dot x minus q is equals to 0, right? So this is the idea. Why? Because the shortest distance, we know we have a linear plane and we have a point. So what is the shortest distance that you are making from that plane? The shortest distance is always perpendicular to the plane, right? It's a vector starting from that point, hitting on the plane, and it is perpendicular to the plane. So these are the conditions for that, right? So now from this you can solve for q. And another information is, in the plane equation, plane of Q has to be 0, right? This is essentially a representation of plane. So you get two equations and you can solve for Q. And then you can get the length of this vector, right? Then scalar to triple product, that's the last thing, right? So now when you were introduced about cross products, so you must have heard about the term area, right? Cross product, cross magnitude of, essentially magnitude of cross product between two vectors is equals to magnitude of the area covered by the parallelogram gram formed by the two vectors, right? Essentially, let's say we have a vector like this v1, we have a vector like this v2, v1, v2. We take their cross product, so that cross product will essentially give us the area spanned by this parallelogram, so this area. This will be essentially equals to V2 cross V1 magnitude, right? So this is the definition of a cross product. Fine. And then the question arises. Now let's say we have three vectors, right? So since we are dealing in three-dimensional space, we can represent these vectors which are linearly independent, right? These vectors. So let's say we have these two vectors like this, and we have another vector like this, right? The question arises: can we do something? Can we say something about on the volume occupied by the parallel pipe found by these vectors, right? So when you join this three-dimensional vectors, you will see that they will form a parallelopipe, right? Parallelopipe. So what is the volume of this parallelopipe? That is given by scalar ripple product, and which is nothing but is equals to area of one face multiplied by height multiplied by height in the direction perpendicular to the plane. This is essentially a classical definition of volume. So you can use this definition to get to the formulation scalar to the product that gives you the volume of this parallel pipe, which is essentially, let's say these are vectors v1, v2, and v3. So this will be equals to v3 dot v2 cross v1. So this will be essentially giving us the volume, right? So how? Again, V2 cross V1 will give you the area of this parallel, this base, right? So this base face, you will get the area from V2 cross V1. And now the height will be, this area vector is perpendicular to this face, right? So you will get some vector like this. When you take its dot product along this third vector, you get the height along that vector, right? So you take the dot product with this and you get the scalar triple product. Now all these things have been covered in the lectures. That's why I'm giving only a small, a very brief, very quick introduction, right? I'm not going into the details, but yeah, these were all the things that were covered in the lectures. Now I have few problems based on these concepts, and let's try to solve these problems. Fine, everyone. Now, till now, anyone, do you have any doubts in any of the concepts covered till now? Please type in the chat box. Please confirm so that we can proceed from here. Am I audible?
Oh, sir, excuse me. Hello.
Yeah. What is the doubt you have?
Sir, suppose if I'm taking 2x plus 3y equal to 8. So this is in
Wait a
3D.
minute. Just a minute. I have some. Uh, okay. Yeah. Now you can speak. Yeah.
Sir, just I have a doubt. Like, if like 2x plus 3y equal to 5, if I'm taking
Hmm.
this one in 3D,
Hmm.
so it represents a plane.
Okay.
So my
So what
concern
you're
is
saying
like
in 3D? What you're saying?
2x plus 3y equal to
Hmm.
5.
Hmm.
So now what I'm visualizing, like its normal vector will be 2 by root 13 and 3 by root 13. Or direction ratio of the normal will be 2 3.
This is a line, right?
Uh, but in 3D, if I'm going to see, so it will be plane, no?
Okay, Z can be extended. Z can be any value, right? Hmm.
Yeah. So
Along
my
that line,
concern
you
is,
will get a plane. Yeah.
so now just now you have said ki its direction ratio will be 0 0 1, but its direction ratio is actually 2 3. Direction ratio of the normal is 2 3.
Okay, fine. But if I am, so this example essentially considers that you are taking a plane that is in the XY plane, right?
Yes, sir.
For
Uh,
this example, this plane is essentially cutting out the XY plane. Can you see
so
this?
it's oh, yeah, that only its direction ratio will be 2 3 of the normal.
Yes, you can see this like this, right? So just draw this line, put x equals to 0. So y is some positive quantity, y 0 x point, right? So you get a line like this. Then when you extend this in 3D, so basically along the z direction, you extend it along the z direction, you will get this plane which is essentially cutting the xy plane, right?
Mm.
So its normal is not 1 0 0 1, right? Now if this was a equation that's it's essentially this plane, this is lying in the xy plane, then you will get normal as 0 0 1.
Okay. So for
Fine.
2 3 5, the direction ratio will be 2 3 only. No, direction ratio of the normal will be 2 3.
That you can check. Yeah, that you can compute and find out
So
the
my concern
normal.
is like if I'm okay, okay, that's only this little bit confusion was there. Ki what how we can visualize that direction ratio here in this case? That only. Okay,
So that
got
will be
it.
perpendicular to this plane, right?
Uh,
That is a
yes,
vector perpendicular to the plane.
got it now. Okay.
So you can what to say? You can always compute the normal of this plane. First, find the normal of this plane, and then put it
This,
basically.
this
Then you will
this so
see
I've
that
got
this
like
will. Mm,
x y will be any vector v vector, and the
mm.
normal vector will be 2 3 vector.
Ah.
Direction ratio of the normal vectors. It is the dot product of both.
So what is this norm direction ratio that you are saying?
Like unit normal only if you multiply with the magnitude of that part, that is direction ratio. Direction
Okay,
ratio
fine.
means the perpendicular the vector where it is in which direction it is pointing it out. So that I think that is direction ratio concept, like x y and 2 3 and 0, it will be direction ratio will be 2 3 0.
Yeah, I'm not sure about this term direction ratio, but yeah, you are getting so unit. So normals are essentially unit vectors. Then in that sense, you will get 2 comma 3
Like
comma 0 by into 1 by root of this magnitude, right? So
okay.
this will be the normal vector. Now
This only I'm.
for direction ratio,
So
I
what is in the
don't know.
bracket?
Basically, you can always say that this is also 4x plus 6y equals to 10, right? So again,
Yes,
this will
yes.
become 460.
Hmm.
So
So
then
that
which
will
is the direction ratio? I'm not sure. Like
no
230
direction
or
ratio will be the
460?
direction ratio is the smallest ratio. That is 2 3 0. That only it will be like
Rational. You're talking about rational stuff, rational
uh, uh,
number.
uh, smallest ratio. Whether
So
it
then
is
what
that
about 30 then? How do you define the ratio here?
direction ratio will be 3 0 0 3 for 3 dimension.
No, I'm not sure. Okay, fine. I don't know from where
Okay.
this term comes on. Maybe if you're looking to some books, then it's fine. Otherwise, yeah. The only thing I'm explaining here is that this will be the normal vector, right? Unit normal vector. That's it.
Okay, sir. Thank you, sir.
Fine. Yeah. Okay. So any other doubts? No one has any doubts, right? So let's move on to the next question. Fine. So let's say p is equals to 1, comma 2 comma 3 and q equals to 3 comma 5 comma 6. What is the distance between these 2 points, right? This is a basic problem. So I am just extending. So now we have seen everything in two-dimensional space. Now we are extending everything in 3D space. So now let's try to solve this problem, right? So all the formulas will be same, nothing will change, right? All the formulations are same, just all the concepts are essentially same, but just are extended to 3D, right? So the first point is in 1 comma 2 comma 3, right? So along the x axis, you cover length 1. Along the y axis, you cover the length 2. Right? This is approximately here. Along the z axis, you cover length 3. So 1, 2, 3, maybe here. Right? So if you join these three, you will get a right. You will get a point, I think here somewhere. Now this is the vector. This is the first vector, and this is the first point, right? This is point P. Right. Then 3, 5, 6 again. 1, 2, 3, and then 1, 2, 3, 4, 5, and then 6 here. This will come somewhere here, right? Then what is the distance between these 2 points? What can you say about the length of this vector, right? So now we can always draw the vector between these 2 points, right? To find the length. So the vector between, okay, sorry, let me write it like this. Vector originating from P and ending at Q, right? So that will be essentially Q minus P. That vector will be Q minus P. Now we know the points 3, 5, 6 minus 1, 2, 3. 3, 5, 6 minus 3, which is essentially, let's call this vector V, right? So now this will be 2, 3, 3. Now I want to find the length of this vector. So length of this vector will essentially be root of V transpose V, right? So this is square root of 4 plus 9 plus 9. So root 22. Fine. So this is a pretty straightforward problem. You all can get to the answer from here also, right? Again, there are other ways to do this. You can always try to come up with geometric proofs, geometric ways, geometrical solutions to these problems. For example, let's say you have a point Q here and you draw a vector to the origin, and from point P you draw a vector to the origin, right? So these are the two vectors, and then you want a vector that goes between them. Then you can simply, what you can do, you can take the vector difference here, right? You can always take the vector difference, and then you will get the vector Q minus vector P, and then again you take the norm. This is pretty straightforward problem. Anyone, do you have any doubts or confusion in this? Okay, fine. Let's move on to the next question. Question number 3. For what values of the scalar C1 and C2 is the vector W equals to 369 a linear combination of U equals to 123 and V equals to 246? Now, let's again think of the definition of linear combination, right? Linear combination. This essentially means a linear combination will be. Okay. So Shiv Kumar, do you have any doubts? Can you type in the chat box? You are raising your hands. Okay. If you have doubt, please type in the chat box, right? Fine. So what is the meaning of linear combination here? I'm saying linear combination of vectors u and v. So basically that will be C1u plus C2v, right? So this is a linear combination of u and v, the vectors u and v, fine. Now the question is, for what values of C1 and C2 you will get that C1u plus C2v is essentially equals to W, right? Can anyone see what I'm doing here? We are getting to the system of linear equations from here, right? So let's try to formulate this. Now this essentially means C1 into 1, 2, 3 plus C2 into 2, 4, 6 is equals to W, which is 369. Fine. Now, let's try to come up in a vector formulation. Now, on the LHS, you can form a vector from these two sum, right? So C1 plus 2C2. This is the first component. So simple vector addition, scalar product with the vector and then vector addition, right? 2C1 plus 4C2, and you get 3C1 plus 6C2. So this is the vector on left hand side, and on the right hand side you get the vector 369, right? Now again you have these two vectors and you are saying these two vectors are same. So just equate the components of vectors on RHS and LHS, right? That's essentially means C1 plus 2 C2 equals to 3, 2 C1 plus 4 C2 equals to 6, and then 3 C1 plus 6 C2 is equals to 9. Right, everyone? Fine. So the question is, how many values of what values of C1 and C2 will ensure that this vector W is a linear combination of the vectors U and V. So we formulated the linear system of equations. Now we want to solve these linear systems of equations. You all know
One
various ways. So Shiv Kumar, do
C11,
you have any
C21,
doubts?
C11 and C21.
Okay, fine. Yeah. Thanks. So I think Shiv Kumar has solved these systems of equation. It says C1 equals to 1 and C2 equals to 1. Fine. So again, you all know a way to solve these systems of equations and you will get to the answer. I hope this works out. Right. So now if this again, the question is what values of C1, C2? There are multiple possibilities, right? The first possibility is no C1 and C2, no C1 comma C2 give you the linear combination, multiple C1 and C2, right? That is infinite. And then one unique, right? One unique C1 and C2, right? So these were the three possibilities, and if you solve these systems of equations, you will get to know which one works out, right, for this system of equations. So okay, so let me just fine. So yeah, now again in the from where you get these three cases, you get from analyzing the systems of equations. Do they have single solution, unique? Three cases, right? Do they have unique solution? Do they have multiple infinite many solutions? Or they have no solution? From that information, you can say what values of C1 and C2 will give you the answers. Fine, everyone?
Hmm. Sir, excuse me.
Yeah,
Hello.
yeah, yeah.
Sir, what I'm observing, like this U and V are linearly dependent.
Yeah, you and we are linearly dependent, right?
So the linear dependent vector can be also written as a linear combination.
Yeah, right.
Like for
Yeah.
2D, so for 2D, so it is not possible because I think we have got that example in 2D. If linear dependent vectors are there, so we can't write the third vector as a linear combination. Something was that no? Like here only linear dependent and independent we can come to know. Is there any
Right.
such
Linear
concept?
dependence essentially means you can write a vector as a scaled version of another vector. That's it.
Means ki all three vectors are in same line. It means ki this. If I'm going to take this W as some other vector instead of
Hmm.
369, if I'm going to take 469, so
Hmm.
we can directly come to know ki since U and V are linearly dependent, so it
Hmm.
cannot be written as a linear combination. Can we come to that conclusion in that point?
Acha, you are saying if
Okay. W vector
if
is
you are saying if W is some scaled version, let's say some scaling factor times
no
U,
no
huh,
no.
huh,
W is already in that multiple only.
Okay.
If W, I'm going to take some other vector like 4, 4, 6, 9.
W is 469. Fine.
Okay. Now what I'm observing ki U and V are linearly dependent. Means it is in a line. That is in one
Okay. They
line.
are a single line, right? Yeah.
So we can't move to the any other vector which is not in the alignment of
Makes
that
sense.
part.
Yeah. Always. Yeah.
So since it is linear dependent, so means ki, it cannot be expressed as a linear combination.
Yeah. Makes sense. Yeah. Fine.
That only I'm
That's
saying.
essentially true. In that sense, because if the two vectors are along a line, you can always span that line, but you can't span other directions. Again, for this problem, I believe that only no single solution exists, right? This will have infinite multiple C1 and C2. If you observe these systems of equations, multiple values of C1 and C2 satisfy these equations. These equations, right? For example, C1 was 1, C2 was 1. Now we can always say other solution, write other solutions as C1 as 2 and C2 as 1 by 2. Again, you get the linear combination, right? So there are infinite possible combinations of C1 and C2 to get to W. Basically, the all the three lines are three vectors are across the same line. So this is C1, this is C2, and this is W. Sorry, U, V, and W. This is U, this is V, this is W. So U, V, and W, right? So they are on the same line essentially. Fine, everyone.
Here,
Do you have any doubts in this?
here W is a linear combination of U and V. No,
Right. Yeah.
U vector is a linear combination of U and V.
Yeah.
So the other person who spoke is getting confused that he's changing the W vector to 469.
Okay.
That 3 he's changing to 4. So once he changes 3 to 4, then the
Hmm.
values which we found C1 equals 1 and C2 equals 1 will not satisfy.
Fine.
Or,
Yeah, that's true. Yeah,
or
that's
in
true.
other words, the W is now not a linear combination of U and V.
Yeah, makes sense. Yeah, right.
Yes. So the other person, one who is talking about direction cosines, in analytical geometry, we calculate L1 cos theta plus L2 cos theta 2 plus L3 cos theta 2 ratios in the analytical
Okay.
geometry. I think he is getting confused that with the vector because here 1, 2, 3 you are treating as coordinates, is it not? Here, when you plot u, vector u, you
Hmm.
take on x-axis 1, y-axis 2, and z-axis 3, and then build up the vector u as a resultant vector. Correct? Means that 1, 2,
Yeah.
3 becomes the coordinates
Uh-huh.
or coordinates actually along x, y, z axis. Multiplied by the unit vectors, it becomes a resultant vector u. Correct? Similarly, V is also a resultant vector with 2i plus 4j plus 6k.
Okay.
Though those two vectors, when you want to find the distance, what we
Hmm.
used to do in analytical geometry is x1 minus x2 whole square plus y1 minus y2 whole square.
Yeah, fine.
Whole square root of that for finding
Yeah.
the distance. That you
Hmm.
showed in the beginning.
Yeah.
What the other student is getting confused is he is asking about the direction. Normal, he's saying. Once he says normal, the dot product becomes zero. U dot V becomes zero. Is it not? When you say normal, you said no. U1, when U dot V is
Hmm.
U magnitude into V magnitude into cosine of the angle between the two.
I think we
So
are getting mixed up in the problems. For now, you're talking about
Hello,
problem one,
hello,
right?
you said
excuse me, sir.
110. 110.
Excuse me. I'm not said that. You're not getting my point. I was just talking about here. I'm not talking about the direction ratio.
Then
I'm not confused in this case. Just
then
I'm
what is
taking.
the
I'm
confusion you
saying
are?
ki both the vectors are in the same line. This I'm saying. and it
No,
cannot.
no.
If
See,
W I'm going to change.
vector is a three-dimensional vector. They are not in the same line. Kindly
In the same
imagine.
direction only. The
No, no,
three are in the same direction.
that's what you are getting confused. U is a
Okay.
vector at some point in 3D space, and V is a vector terminating at some point in a 3D space.
No, wait,
When you
wait, wait,
join those two, okay,
wait,
that
wait,
P
wait,
and Q,
wait.
that
Listen,
becomes
no,
a straight line for you.
no,
That
wait,
is the distance.
no,
Got
no.
it?
1, 2, 3 is the point in 3D. Do you agree?
P. That is P. That is P.
Okay,
You.
Point P.
so
Point
guys,
P.
just let's stop here, right?
Because
So
yesterday
let
I
let me
registered for
let
the
me
exam. From exam point of view, I've become serious now. That's why I'm talking
okay.
all this. Yeah.
Yeah, right, right. So let
Hmm.
me just clarify both of your doubts again and one to one, right? In one to one fashion. We have only two students here, so we can consider this doubts first. So, like, first, Shiv Kumar, what doubt do you have? That I can explain right now, right? Let's not
I don't have
get
any
into.
doubt. The guy who asked, that is
Okay,
Satinder
fine.
Tiwari.
So
So
Satinder, what doubt do you have?
Sir, I don't have any doubt. Like, sir is getting confused. I think he was not getting my point. He have cleared my things. We have the discussion just now. Like, U is the point.
Uh,
V is another point in 3D.
no,
So
no, you have to
I'm
Right,
use
saying
but again, just look
Satinder.
at the question problem statement,
Satinder,
right?
you have to use
So
the right
we,
words. U is a vector. P is the point.
yeah, W
U
is a
is a
vector and U is also a vector and V is also a vector, right?
so
and
The
this one
question
is
P
says
is the
these are
point.
vectors, these are not
Yeah,
points, right?
these are not points.
okay. If these are the vectors, so in terms of the vectors, like U is a vector 1, 2, 3,
Yeah,
V is a vector 2, 4, 6.
yeah.
So they are not in the same direction.
They are in the
Why,
same direction,
why you are
basically.
telling same direction? It's a linear combination. C1U plus C2V.
So if I'm going to change W, so it will be expressed as a linear combination.
No, W is C1U plus C2V. Now, instead of values 111 for C1 and C2, it will become a different value.
Okay,
That's all.
okay, please, both of you just
So
stop right
let's
now,
solve
right?
it. Let's
Okay,
solve then by
both of you,
taking
please
W
stop,
four
okay?
six
So
nine.
I'm
Let's
muting you
solve.
guys, right? I'm
Okay,
muting.
I'm not fighting. I'm
Yeah, I'm muting both of you. I'm just explaining what I know about the problem. Again, if you have a doubt, you can ask me later on, right? Fine. So the thing is, U is a vector, V is a vector, and W is a vector. Fine. So when we say we have 3 numbers representing a vector in 3D space, this is a vector that originates at the origin, right? And goes towards that point, points in that direction, and goes till that point, right? This is a ray. So it goes from 0 to 0,0,0 to 1, 2, 3. Let's say in the 3D space. So this will be your vector U. Now again, you take a vector v. This again originates from the origin and it goes to the point 2, 4, 6, right? And this is the point. This will be some point 2, 4, 6. That will be vector v. The only thing I am saying is both of them lie along a same line. If you were to draw a line passing from the origin passing from the origin, either you extend the line along the vector u or along the vector v. Both of those lines are the same lines, and these two vectors are essentially aligning on a same line. They are spanning a same line, right? Now in this case the vector w is also along this line. So essentially any linear combination, there are infinite many possible values of c1 and c2 that will essentially give you vector w, because all three vectors are essentially, if you extend them and to find a line from that extends to the infinity on the both sides, all the three lines are same. They are the same lines. So that's why you will get infinite many possibilities of c1 and c2. That's it for this problem, right? So let's not get confused into vectors, points, and notions. So this is all idea. Vector is something that goes from the origin to that point. That's it. Let's not get
no,
confused
sir.
in.
Actually, I've asked that part. If W, if I'm going to take as a 4, 6, 9.
Yeah, right. Then this will
So
be a vector something like this, right?
yes. So
And then
can
you
it?
can't get any linear combination of u and v to get to w, right?
Uh,
That's
so,
the
so,
thing.
so
That's
that's
it,
only
right?
we are discussing. That's only we
Hmm.
are discussing that part.
So is this clear now? If you have any doubts. Shiv Kumar, do you have any doubt? And Satinder, I hope the doubts are clear, right? So this is all
Hmm.
what we have in this.
Yes, sir. That only I was saying. If it is 469, so I think that will be not because two are in the same direction and we can't move in the other direction. So
Right.
linear combination. That only I was saying. I was not saying
Yeah.
something else.
Yeah.
Okay,
Fine.
sir.
Shiv Kumar, is this clear? So you can type in the chat box also if you want, right?
Which one? Which one you are telling? The
This
one you
problem, is this
explained
clear?
is the one you explained is very clear. I
Ah,
don't have
fine.
any doubts. Mm.
So let's move then from here, right? We can proceed, right?
Yeah, you can proceed. No problem.
Fine. Thanks. Okay.
Thank you very much.
So let's move on to the question number 3, right? So let's say u equals to 1 comma 2 comma 3 and v equals to 1 comma 2 comma 1. Again, these are two vectors, right? So then the cross product of these two vectors is, right? So this is a simple problem of cross product. We all know the formula for cross product in the 3D space, right? So there are two ways to solve this problem. One is from the knowledge that you don't had you had before this course, right? The knowledge that you had before this course simply by understanding geometry. So now let's say you have vector one originating from the origin O, right? And going to the point 1, 2, 3 in the Cartesian plane. And then again, you have some vector originating from origin 0 and going to the point 1 to 1, right? And then we know by the definition of cross product that it represents the magnitude of the cross product represents the magnitude of the area occupied by the parallelogram found by these two vectors, right? So now one thing you can do, you can try to compute the area of this parallelogram. Fine. So let's say these two vectors form the edges of this parallelogram, the two edges of this parallelogram, and then try to find the area of this parallelogram using the formulation length of the base, right? Length of base multiplied by, okay, let me just, so the area would be length of the base, right? Base edge multiplied by length of height, right? In the direction perpendicular to the base edge, right? Now, this is one way you can do it. You can use geometric and every geometric information that we know about these vectors, right? You can always find the length of this base. You can always find the perpendicular height, the height from this base to the opposite side, which is essentially the perpendicular length of this point 1 to 1 from the line 1 to 3, right? You can always solve this and you will get the area of this these two vectors, and then this will be essentially the magnitude of the cross product that we are trying to find out, right? Now another way to do this is simply use the formulation for cross product that we already know, right? So how to do the cross product? You build up a matrix, the cross product matrix. So the first row is I cap, j cap, and k cap for the 3D space. Then for the second row, you put in the first vector, which is 1, 2, 3, right? 1, 2, 3, and the second vector, which is 1, 2, 1. 1, 2, 1. So you build up this matrix and then you find the determinant of this matrix. Right. So now let's do this. The determinant of this matrix is I cap multiplied by 2 minus 6, right? 2 minus 3 to just 6 minus j cap multiplied by 1 minus 3, right? Plus k cap multiplied by 2 minus 1. Fine. So this is essentially minus 4 I cap plus, yeah, it becomes plus 2 j cap. So this will be the cross result of cross product between these two vectors. When you take the so this is essentially u cross v, right? So this is a vector. Now when you take the magnitude of this vector, you will see that this magnitude of this vector will be equal to area of this parallelogram. Fine, everyone, do you have any doubts in this problem? I hope this is pretty simple problem just for introducing the concept for 3ds. Fine. Again, now let's say if you had the magnitude of the area of this parallelogram, and then from here you want to get to this vector, right? How to do this? You can always we all know we can use the right hand thumb rule. I hope you remember this. So you put your palm like hand on the one of the vectors. So you put your hand in this direction such that your thumb is pointing upwards, and then move towards the move your palm towards the next vector, the other vector. So the direction of your thumb will give you the direction of the cross product, right? So in this case, you can simply find the normal of this normal of this plane. You have to find the normal of this plane, and that will give you the direction. And when you multiply the area of this parallelogram and that direction vector, you will get this the result of this cross product. Fine. So this is something just a basic on cross products. That's it. Anyone do you have any doubts? Please type in the chat box. Fine. So let's move on to the next question. Let u is equal. So let's say we have three vectors: vector u, vector v, and vector w. Then the question is, what is the volume of the parallelepiped enclosed by the vectors? Again, this has been covered in the class lecture itself, and we know the solution to this is essentially u dot product with v cross w, right? So this is the answer that you will get if you want to find the parallel volume of the parallel pipe, right? This is essentially scalar triple product. Fine. Now, how to get to this formula? So this is something that we are just writing that this will be the answer. But how to get to this, right? So now let's try to see how to get to this. So let's form the parallelogram base formed by the with edges as these vectors. So let's take this vector v here and then vector w here, right? So these vectors will form a parallelogram like this in the plane, right? Now you can successfully compute the area of this parallelogram using the cross product formula, which is essentially v cross w, right? And this is essentially pointing upwards. We all know that, right? This area is essentially pointing in this direction, right? Now you draw the third vector minus 4 comma 2 comma 0. So let's say it is in this direction, right? So this is the third vector, which is essentially u, right? So now what you do, you form a parallel pipe from these three edges, right? So you can form a parallel pipe from these three edges. Sorry, right? Now this will be your parallel pipe. And again, you know what is the formula for the volume of this parallel pipe, right? So what is the area multiplied by the height, right? So area in the direction of this vector, So this is essentially u dot, right? You take this value and you will get to the answer. Is this clear? This was covered in the class, everyone. Fine. So how to get now again, you can do the computation and you will see that this will
I
work
have
out.
a small doubt.
Yeah, yeah,
This u vector u
yeah.
is minus 4 to 0. That means it is entirely in the xy plane, correct?
Vector u, right? Yeah.
And v cross w, when you compute,
Hmm.
it will be it will not be in the xy plane. That
Hmm.
vector product will result in the uh, uh, act direction or act in the z direction, correct?
Not z, right? Because
That
let's
is a.
do this computation. IJK 11021. Is this coming out to be in the z direction? 1 minus 0. No, it is not, right? 1 minus. This is 1 square cap into 2 minus 1 1. Right, this is not a vector in z.
It is
It's
I'm
a
a
vector in the 3D space, which is
3D
not
space.
only in the Z direction. It has
3D
some
space.
component along the X, Y, as well as Z, right?
And then the vector u is entirely in the xy plane, correct?
Yeah, right.
Ah. So when the vector u and vector v, of course, is not entirely perpendicular, so dot product will exist.
Right. Yeah.
Yeah, will exist. Yeah.
Fine.
Thank you. Yeah.
Okay. So now, let's, since we have done this, we should also proceed with this. So
So,
this is
excuse
V.
me,
Yeah.
uh, I have not seen that video yet. This one, volume of parallel piped one. This one video still I have not seen. So I
Okay.
have a doubt uh, base into height. Base into height is the volume. Area of the base into height. That is the volume. So V
No, no.
cross.
Ha.
Hello.
Yeah.
Just I want this expression. Can you explain U dot V cross W how we have got like
Hmm?
concept behind this?
So
And one more thing,
V cross W gives you the area of the base, right?
area of the magnitude V cross W magnitude will give the area of base. I think so. Mm.
Right. Yeah, that magnitude will give you the area of base, right? Yeah.
And then height. So what will so that is the area of the base. So
Yeah.
height will be represented by what, sir? This I'm not understanding here.
So
Like
essentially, now let's look at this problem like this. So let's say you have this plane, right? And you have some perpendicular vector to this that is essentially representing this area of this quadrilateral, right? Fine.
yes, sir.
And then you form a volume from this using some vector which is not perpendicular to this. Fine.
Yes, sir.
So now what is the length that this vector, the vector which is not perpendicular, making along this orthogonal direction? That is your height, right?
Got it, sir. Now
Got it? Again,
got it.
simplest way is consider a cube like this. The simplest way is consider a cube. And you can verify if this is true, even if it's true or not. You can always verify this. So let's say you take a cube. Um, let's say this is the cube that goes from origin 0 comma 0. This is 1 comma 0. Sorry, 2 comma 0. This is 2 comma 1, and this is 0 comma 1, right? So let's say this is the base, and then from here you make a cuboid, right? Extend by length 1 in the third direction along the z-axis, right? You form this cuboid. Now, what is the volume of this cuboid? You know, it will be 2 into 1 into height, which is 1, right? And again, when you use this formulation, you will get that the area will point in the direction 0, 0, 1 with some magnitude. And then your height is also, your third vector is also 0, comma 0, comma 1. So they both
Exactly.
align, right?
Yeah.
This makes sense, Satinder, right?
2 into 1 is 1.
Yes. So
2 into
So
1 is 1
one
into
more
2.
doubt is there. If
yeah.
volume is coming out to be negative, so what does it mean? Like area negative to flip. Area negative to means that is the concept that the it is
So
we take magnitude, so that will not come
volume is a scalar, right? Volume is a
no,
scalar.
it comes out to be negative.
In the dot product, it can come out to be negative. You simply take the magnitude of it, which is a scalar of
So
magnitude of a
like
scalar is absolute
in
value.
exam, if it comes we have to calculate the volume. So
Hmm.
what should we write? If my answer is coming in minus, so should I keep it minus or should I take the absolute value?
Absolute value, right?
Like this answer is coming out to be -6. Now just this question I've solved. I
But
think minus.
volume is something, yeah, right. But volume is something that is considered to be with dimension, with something that is a scalar. And volume cannot be negative. In terms of area, the area can go negative, but it doesn't mean that it is occupying negative area. It's just that you are
Flip.
choosing some basis, and in
Uh-huh.
that basis the
Hmm.
cross product is coming out to be in direction of the negative direction. But
Hmm.
essentially, when you take the magnitude is always positive quantity, right?
Okay. So, because when we are finding this one, like volume, so it comes
Hmm.
out with -6. So ultimately, we'll write the absolute value of -6 for this question.
Yeah, right. Yeah, yeah.
Thank you, sir.
Okay. So, anyone do have any doubts? Shivkumar, if you have any doubts.
Doubt
Fine.
is not there, but one thing is, when
Hmm.
you calculate the volume,
Hmm.
since the equation says dot product, the
Hmm.
ultimate will be a scalar only, no?
Yeah, it will be scalar, right? Yeah.
Dot product will result in scalar.
Yeah.
So when it is scalar, take the
Hmm.
absolute value, that will be the volume.
Yeah, that is the volume. Yeah. Fine. So let's move on to the next question. Find the orthogonal distance between the two planes with normal 1, 0, 0, where the point P and Q lie on the first as well as second plane, right? So let's see if a orthogonal distance essentially exists between these planes or not, right? So that will the first question that we have. So let's go to the point P. So the point P is essentially 0 comma 1 comma 1, right? So x is 0 in yz x basis you get this point. So this is in the yz plane, right? This is in the yz plane. So this is x axis, this is y axis, and this is z axis. So this is your yz plane, and the normal is set to be 1, 0, 0. So normal is along the z axis. So your plane will look like this, will look something like this, that passes through this point. This point is essentially 0, 1, 1. Essentially, this plane represents z equals to 1, right? Z equals to 1. This plane essentially represents z equals to 1, right? Then the second plane again. So let's move on to the second plane, right? And z, right? And then you have a normal 1, 0, 0. Okay, 1, 0, 0. Sorry, sorry, sorry. Yeah, I made a mistake here. Okay. So it's along the x-axis, fine. Okay. So let's say this is your basis and you have the point 0, 1, 1. So this is this point in the YZ plane. And I'm saying the normal is along the x-axis, right? This is x-axis, this is y-axis, and this is the z-axis. So your plane will be essentially the YZ plane, right? So this is the plane that we are interested in right now. So this is the YZ plane, fine. So this is the YZ plane. Now the second plane is again a plane that passes through the point 2, 3, 1. So let's plot the point 2, 3, 1 will lie somewhere here. So let me use the black pen here. So this is the point 2, 3, 1. And again, this plane is have a normal in the direction 1, 0, 0 along the x-axis, right? So again, this will be a plane parallel to the previous plane, and you get this plane. Is this visible, everyone? Can you see the distinction between the two planes? So both the planes are parallel, right? You can see those planes. Fine, everyone? So the first plane cuts the x-axis as 0. The second plane cuts the x-axis as at 2. Fine. So this is the 0, and this plane essentially cuts the x-axis as at 2, right? So, okay, so let me make the figure a bit more clear. Fine. Right? This was inside and x-axis. So let's say it is hit. It is hitting at point 2 here, right? So yeah, this is how it looks like. So this is the point 0 here, origin, and yeah, and this is the point where it hits the second plane, which is 2 comma 0 comma 0. So we all know the perpendicular distance is 2, right, everyone? Geometrically we can see the answer is 2. Is this clear? So what I have done, I have simply drawn the planes in the 3D space and tried to find the perpendicular line between them and get the length of that line. So, orthogonal line, so a line that is orthogonal to both the planes, and then find the length of that line. So essentially the distance between these two parallel planes, right? So the distance between these two parallel planes. Fine. So everyone, can you get this? Can you see this? That this distance is essentially 2. First of all, is this clear what I've done here?
Yes, sir.
Fine. So Shivkumar, is this clear?
I mean, since P is 0, 1, 1 and Q is 2, 3, 1, the
Hmm.
distance along x-axis is 2 minus 0. So you are telling the distance between the planes is 2.
Hmm.
Like that you're telling.
Yeah, the thing is, there are two planes. They are
Hmm.
passing through some 2 points, right? And I am
Hmm.
saying both of them has a same normal. So both of them has
Oh,
same vector, which is orthogonal to both the planes.
same
Now, if
normal
this
means they are
these
parallel.
conditions are met, they are parallel, right? We agree
Parallel.
with this.
And the
Do we agree with
difference is
this?
in the x-axis, that
Yeah.
is 2 minus 0, which is 2. So you're telling the distance between the two planes is 2.
Again, yeah, right.
Oh, no.
Right.
So
This is
no need to
clear.
calculate anything, just the
Yeah, yeah, yeah. Just
understanding
geometrically, you
of
can get to the answer.
get to the answer. Okay, thank you.
Yeah. Again, the thing is, this is the only case where you will get a vector orthogonal to both the planes, which are same in the pointing in the same direction. If two planes are parallel, their normals will be in the same direction, right? We agree on this. And this is what property I'm showing here. So these are two parallel planes. And now using some geometry, we can figure out the length very easily. Another solution would be take the point. So again, another solution, what you can do is, so let's consider this as the plane that passes through the point, let's say 0, 1, 1, and we have a point 2, 3, 1, point 2, comma 3, comma 1, and this plane has a normal 1, 0, 0. The normal is 1, 0, 0. Then what you can do, let's say this is the origin. So what you can do, you can try to find the orthogonal projection of this point on this plane and try to find the length of this point, length of this vector, right? We have seen this also in the lectures. Fine. So we can also use this formulation, this information to solve this problem.
Is
So
it
that,
similar to what we find the component of a vector along an axis or a plane,
yeah, right.
and then dropping a perpendicular to that, finding geometrically the distance and knowing the
Yeah.
answer?
So
Yeah. Okay.
So essentially, you are trying to find the foot of the perpendicular line from the point 231, that
Oh,
trying to find a point in the plane represented by that passes through this point and have this vector, normal vector as this, right?
yeah.
And such that the point is perpendicular, the vector between the point and the foot of this point, the projection of this point on the plane, this vector is essentially orthogonal to this vector, this plane, which is essentially in the direction of 1 comma 0 comma 0.
Yeah.
Then you will always get this vector, and then all from this vector you can get its length,
Yeah.
which
Good.
I'm sure you will get to be 2. You can solve this,
Yeah.
right?
Very nice.
Yeah. So again, this is question number 6. This is a question that we covered in the previous session also, but now since we are extending everything to 3D, why not do this for 3D also? So in the previous session, what we did is we solved a similar problem but only for the 2D plane. Now let's think of the 3D plane, right? 3D space, right? So now let's draw our 3D plane. I hope the figures are clear, and this is the answer. Let me write here. So this is the answer, right? So this is the answer. Answer is 2. So this length is 2, right? Yeah. So let's move on to the next question. Now again, let's extend the reflection problem to 3D. So this is axis x1, this is x6, x2, this is the axis x3. And now you have some three-dimensional vector. Let's say we have this vector u that goes from origin to the point u1, u2, u3. Now, what is the reflection of this point, this vector u, about the x1 axis in the x1, x2 plane? So how would it look like, right? So you, let's say this was the plane. Uh, so what I'm doing is I'm basically rotating the plane a bit so that we can see both ends of the point. I can also do this here also. Hmm, right. So now let's plot this vector as if it is coming out, right? So let's take this vector, right? So let's take this vector u. The vectors are same. You can choose any vector you want, right? I want the reflection of this vector about the axis x1 in the x1, x2 plane. So this essentially means take the projection of this vector on the x1, x2 plane, fine, and then reflect it about the x1 axis. So you reflect it about the x1 axis, you get here, and then bring back to the 3D space. So you will get this vector. This will be the u reflected, right? So this is a geometric idea what I am saying here from this problem. Is this clear? Is the problem clear, everyone?
U1, U1, U2, U3. Is
Hmm.
it like U1 is along X1, U2 along X2,
Yeah, right.
and U3 along X3?
Yeah,
Correct.
yeah.
And then when you take the reflection about the X1 axis,
In
U1
the
becomes
X,
minus U1, correct? U1 becomes minus U1. Am I right? When you take the
no,
reflection.
no, 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 no.
Oh,
U2 becomes minus U2 because you are taking the reflection around the X1 axis, right?
about the X1 axis, what will be the coordinate will be
Okay, right.
U2.
Again, the problem is, so let me just restate this problem. So let me change this problem a bit. So it's quite getting confusing for the 3D case. So let me change this axis stuff entirely and let's get the reflection u about the plane. So let's say the plane, what plane we can use? We can say z equals to 0, right? About the plane z equals to 0. Now the problem is quite simplified, right, everyone? So ignore the previous problem. It was quite confusing and the problem did not make sense entirely. So let's take this problem, right? Now again, this is your plane z equals to 0, right? This is the x1, x2 plane. So let's take the xy axis itself, right? And z would have been somewhat in this direction, right? But I'm talking about the plane represented by the equation z equals to 0. This is essentially the xy plane. Everyone agrees on this? So
Yes.
this is the xy plane, right? Xy plane. Now you have some vector u. So let's take this, some vector u, right? So there are two cases, right? Either u3 is 0, either u3 is 0, that is the vector u essentially lies in the xy plane, right, everyone? So you will get then the answer will be a same vector, right? If u3 is 0, you should get same answer, right? Because if it's in the plane and you want to reflect it about the plane, it's essentially nothing. It's doing the same thing, right? Is this clear? If you, so let me make up the cases. Case 1, u is in xy plane, right? Then what happens? Reflection of u is equals to u itself. Is this clear, everyone? So geometrically also you can show this. This is very straightforward. Fine. Do you have any doubts, anyone, in this case?
No doubt.
Fine. Now case 2, u3 not equals to 0. So u is in all three, right? XYZ plane. So what happens in this case? So you have some vector u like this, right? This is the z axis. You want to reflect about the xy plane. So the angle it is making from the xy plane, it will make the same angle in the opposite direction about the xy plane, right? So let me show how this looks like. So this will be u reflected, right? This will be u reflected. Fine. This will be u reflected, and let's see how to get to this, how to get to this answer, right? So so we all know that we have some projection, orthogonal projection of this point. So let's draw this vector, right? Let's draw this vector between u to u reflected. So let's take this vector between these 2 points and let's observe one thing. Since we are talking about reflection, right? Mirror reflections, this vector will be perpendicular to the plane z equals to 0. Everyone agrees on this?
Yes.
Fine. This is the definition of reflection basics, right? Now the question is how to get to this vector. The easiest way is set the z component to negate the z component, right? So you will get u1, u2, and minus u3. This is the simplest way to solve this.
Yeah.
Your reflection of u along the xy plane. Is this clear, everyone?
Yeah.
Fine. And again, how to form a matrix from this. So let's say you have matrix M and you have vectors u1, u2, u3, and you are getting the vector u1, u2 minus u3, right? So what you can set it up as 1, 0, 0, 0, 1, 0, 0, minus 1. So this will be your reflection matrix. Fine. So this matrix does the job. This is the answer. Answer is 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Right. You can think of it like this. Is this clear? Does this
Yes.
work?
Yes. Yes.
Everyone, do you have any doubts?
No doubt.
Fine. Satinder, do you have any doubts?
No, sir.
Fine. So let's move on to the next question. Right. This is quite interesting problem, right? So let's pay attention to this. So given two independent vectors u and v, that is these belong to the 3D space, and a vector b which is 4 to 1. Find the shortest distance between the points between the point b between the point b and between the point b. Point is essentially, okay, let me clarify this statement here. Between the point at end point of vector b, right? And the plane spanned by the two vectors, given that u dot b equals to 3 and v dot b equals to 2. Again, we will try to solve this problem. So we have two independent vectors, u and v, and we have no information on them. So let's assume some vectors. So right? So let's assume this is our vector u, and let's assume this is our vector v, right? Now we all know that they span a 2D space if they are independent. And since we are saying they are independent, the question says, so they span a 2D space, right? So this is the spanned plane from these two vectors, right? Sorry. Ah, so they are spanning this plane. So, right. So this plane we are spanning. Huh, fine. Now we have a vector. So let's say this was the origin, right? Let's say this is the origin for this space. So this is the origin, right? Now we have a vector that originates from the origin and goes to the point 4 comma 2 comma 1, right? So let's take this vector. So let's say, okay, let me move everything. Yeah, fine. So now this is the origin, and let's say we have a point that is in the 3D space, which is 4 comma 2 comma 1. And now when you draw a vector starting from the origin to this point B, you will get this vector B, right, to this point. Fine. Is the problem clear, everyone? So, okay, is everyone,
No,
is the problem clear?
no, u dot b is equal to 3 is a dot product.
Yeah, right.
That is magnitude u into magnitude b into cosine of the angle between those two.
Yeah.
That is
Let's
higher.
let's go to that at later stage. First, let's think if we all of us are on the same page on the problem description. Is the problem clear?
So you want the shortest distance means you want analytically or geometrically?
Anyway, you will get the shortest distance. Analytic, if you use any other method or if you use geometry, you will get the shortest distance. That will be
Okay.
the length of the perpendicular from this point to this plane. Right? So
Yeah.
you have a vector b that goes from origin to the point 4 comma 2 comma 1, and you
Yeah.
have a plane spanned by two independent vectors u and v, and you want to find the shortest distance of this point from this plane. But again, in this question, you are not given the information of the plane is not given completely. We only know this information that u dot b is 3 and v dot b is 2. Now, if you were given the equation of the plane, this was very straightforward problem that you have done in the classes, but this information is not given. You only know that the component of b along u is 3 and component of b along v is 2. Given u and v are let's call them unit. Let's take them units. These are unit vectors. Fine, everyone. Is this clear? Satinder, is this clear? U and V are
Yes, sir.
unit vectors. U and V are unit vectors, right?
Yes, sir. Yes, sir.
So
Yes,
now
sir.
how to find the shortest distance? The shortest distance, we know that it will be the vector going from point B to a point, let's say Q in the plane such that the vector Q minus B is orthogonal to the plane, right? So the vector Q minus B dot the plane dot our plane will be 0, right? So now we can always say Q minus B dot vector U will be 0 and Q minus B dot vector V will be 0, right? Can we say this? Everyone, do you agree with this information?
Because the angle is 90 degrees.
Yeah, right, everyone? So now just try to get to something from here. So Q, so this is a vector Q dot U minus B dot U is equals to 0. And again, Q dot V minus B dot V equals to 0. Now Q is in the plane of spanned by U and V, right? So we have these two equations that we know. The third equation that we know is Q is essentially C1U plus C2V. How? How we are able to say equation 3? Anyone, can you explain me? Why we can write this third information? I hope the first two
It
informations are
lies in
clear,
the UV plane.
right? So it lies in the plane spanned by the vectors u and v, which are unit vectors and independent. So you can always write vector q. So this is our vector q, right? So this is our vector q, and we can always write our vector q as a linear combination of these two vectors, right? So we have three equations, and let's try to get to the answer, right? And we have some information also, right? So let's take equation one and try to solve. So q dot u essentially means c1 u plus c2v, right? Plus c2v dot product with u minus b dot u. We all know the value of b dot u is 3, right? Minus
Yeah.
3. This is equals to 0. Now from here we can say uh, c1 dot u will be c1 into 1. So u dot u is essentially 1, right? Plus c2 into v dot u is equals to 3, right? Okay, let
Yeah.
me add a page. Okay, we are here. This gives us C1 plus V dot U into C2 equals to 3, right? This is equation. Let's call this equation a new equation in Roman numerals, equation I, right? Now let's try to get to somewhere from equation. So this was 1 and 3. This was using 1 and 3. Now let's use using 1 and 3. Now let's try to using 2 and 3, using equations 2 and 3. We can say equation 2 says Q dot V. Again, Q is C1U plus C2V dot V, right? Dot V minus B dot V. We know the value of B dot V is 2, minus 2 goes to 0. Again, solve this. This case gives C1 U dot V plus C2 V dot V is equals to 2. Now V dot V we know 1, because V dot V is essentially 1, since we are dealing with unit vectors, right? So C1 U dot V plus C2 is essentially 2. Now let's call this double I, this equation double I, right? Now, can we get to somewhere from this? Now, the quantity we want to compute is the length of the vector q minus b, right? We want to compute norm of q minus b, right? Norm of q minus b. Let's write this again. So q is essentially c1u plus c2v minus b is essentially 4 to 1, right? B is so 4 to 1. Let's write this. Now you will get a new vector like this, and you want to find the norm of this vector, right? Okay, now what we can do is just take the value of v dot u from 1. So let's do this. So use I to get v dot u is equals to 3 minus c1 by c2. 3 minus c1 by c2. Put in double I, right? Put in double I, which is essentially saying c1 into u dot v, right? This is essentially 3 minus c1 by c2 plus c2 is equals to 2, right? So now you get one single equation in c1 and c2. Fine. So where we can go from here? Let's see. So 3c1 minus c1 squared plus c2 squared equals to 2c2. So you get C2 squared minus C1 squared plus 3C1 minus 2C2 equals to 0. So we get this equation. So this is two variables, one equation. And again, when you try to build up the norm of this vector, right? When you try to build up the, so let's call this 3i's, right? So equation 3i, right? This will give you another equation, and use these equations, use them to solve for C1, C2, and then get the norm, right? But again, right, what I'm doing here is I'm stopping here because this is getting too lengthy, right? And we don't want to do this. So this is one way you can solve this problem, and I'm pretty sure you will get an answer from here, right? The another easy way, let's try to think of that geometrically, since we are doing everything is geometrically. So let's try to, everyone see that we from here we can get to the answer. First of all, I have built up one equation. You need one more equation that you will get from triple I, and you can solve this. Is this, everyone, do you agree with this? So I can also give you a hint, right? When you try to solve this 3 will essentially say, so this equation 3 will say C1U plus C2V minus B dot C1U plus C2V minus B, right? Now, when you take the dot product, you will get C1 squared plus C1 C2 into U dot V plus minus C1 U dot B. Now U dot B is known. This is a known quantity, right? Again, you expand this and you will see that you will get an equation that will get to you to the answer, right? This is how you can proceed from here. Everyone, do you agree with this solution? I am going to show a more elegant and geometric solution that is really easy. Everyone, do you agree with this? Can you get to the answer from here?
Is it that we end up with two quadratic equations?
Yeah, but you have two equations and two unknowns. You can solve them, right?
C1 and C2. Okay.
Right.
Yeah.
So now let's get to the geometric point of view. Now, what we can observe here is our question says the projection of vector B along the unit vector U has length 3, right? So let's take the dot product of B and U. You will get some magnitude along the vector U, right? So let's take this vector, right? This vector as B dot U along the U direction, right? Everyone, do you agree with this?
Yeah. Yeah.
Similarly, you take the dot product of B with U, V, right? You get to this vector. This is B dot V in the direction of V, right? Now, when you add these two vectors, you geometrically, you can see this is essentially the sum of these two vectors is this vector Q, right? So you will see geometrically that Q is essentially B dot U along U plus B dot V along V. Everyone, do you agree with this? I think no one is
That
agreeing
is
here.
Yes, yes, yes.
added, like
Okay, okay.
adding the parallelogram,
Yeah, again,
comparing the
same thing.
parallelogram. Yeah.
Yeah, same thing. Now, how to get to this? You draw a vector perpendicular to the vectors U and V, which is orthogonal to this plane. Then you can always write B in terms of three basis vectors, U, V, and some ortho perpendicular vector, right? And we know the component along U and V are these components. And we know that when you add these components, you get to the orthogonal projector on this plane. Fine. This is everything from the definitions. Everyone, this is clear?
And these components are in the UV plane.
Yeah, yeah.
Yeah. Yeah.
Fine. Now you get to the plane vector q. Now you only needs the magnitude. Now let's use more geometry here. Why not? So now you know this vector zero origin to q. This is this quantity. Now you know the length of these. This will be. You can always compute the length of this vector, right?
Yeah, yeah.
The length you will get is square root of 5, right?
Oh, that is 4 square plus.
Okay, yeah. So the question also misses one more information. U and V are orthogonal, right? U and V are orthogonal. So then you will get this picture. This will be root 5, right? Is this clear?
U and V orthogonal, meaning like XY axis. Yeah.
Ah, right. Yeah, same.
Mm.
So this length is then root
Uh,
5. Yeah.
sir, how it will be root 5? This I'm not getting.
Okay, so are you agreeing that the vector q from going from origin to the point q will be b dot u in the u direction plus b dot v in the v direction? Do you agree with this?
Yes, this so I agree.
So now what is q dot q? So b
Uh,
dot u squared, right?
yeah.
Plus b dot v squared, right?
Yes.
Do you agree with this? Because these two are orthogonal to u dot v and v dot u will be zero. And then for the norm, what we do, we took the square root of this quantity. So now
So
the
this
square
will be
root of
9.
this is
So this 9 plus 3 square is 9. 9 plus 4
okay.
is
Yeah.
13.
Sorry. Yeah, I made a mistake here. So this is 9 plus 4, right? The
Yes, sir.
root of 13. Yeah, fine. Thanks. Yeah. So now you know that this is a right angle triangle with the base having length root 13. And again, you know the vector VB, right? So you know that this length will be square root of 16 plus 4 plus 1, which is square root of 21. Now you only need to find the length of height. You know the hypotenuse, you know the base, you can compute the height, right? So this length will come out to be root 21 minus 9, right? Which is sorry, root 21 minus 13, right? Sorry. Root 21 minus 13, which is root 8. Is this clear, everyone? Fine. So this is geometric solution, very simple. Now in algebraic, what you have to do is you have to simply substitute these quantities u dot v to be 0, and you will very quickly get the answer. You will essentially get C1 equals to 3, and then from there you can set C2, you can compute C2, and then you will get the same answer. C2 will be 2. So you will get C1 equals to 3, C2 equals to 2, and you can solve this. Fine, everyone, is this problem clear? So this was something that I tried to formulate a problem that does not give you the explanatory equation of the plane, but gives you some information from where you can get to the answer. Right? So these are some tricky problems. So you should think of linear algebra like this also. Fine. So it's
Uh,
almost,
sir,
yeah, yeah.
for that equation, so there only we are getting the answer C1, C2 in the beginning only.
Ah,
We
yeah, yeah,
have the equation no? C1 mod u square plus C2 u dot v. We have in the equation equal to
yeah,
3.
yeah.
So there u dot v is 0 if you'll put so, and mod u is 1. So C1
Hmm.
directly we are getting 3. No need to go over there.
Yeah,
Uh,
right. You directly get C1 equals to 3 from here itself.
um, that what I'm saying.
Fine. Anyone, do you have any doubts here?
I have a doubt. Since the course is through geometry, graph
Hmm.
sheets will be provided to construct and give the answer.
I'm not sure. I cannot tell anything about the course curriculum because I'm only here to take the tutorials. You can talk to the NPTEL team, email them and ask them about these logistics
Graph
details.
sheets won't be provided. Only
I don't know about these
we have
details. You
to,
can
like
ask.
you're doing calculation, we have to do the calculation and then show.
I don't know how the examinations are set up. So I'm only here to solve these problems for you guys.
University exams graph sheets are provided in the
Okay.
university exams. Graph
Okay.
sheets are provided. I don't know what about NPTEL.
You can ask the NPTEL guys for this, right?
Okay.
Fine.
Yeah.
So it's
Thank.
already 7:52, right? So we have only 8 minutes left in the session. So let's take this 10 minutes for question and answering. So I have few more problems that I will cover in the next session, right? So in the next session, I will first solve these three problems and then we'll proceed to the next problems. So now, till now, do you have any doubt in any problem? Should I explain any other concept or should I explain any other answer again? So these are the topics that were covered in this week. You can ask any doubt right now.
This many years I have taught electromagnetic
Okay.
where this vector calculations comes a lot in that.
Hmm.
So, which book is preferable for all these studies as per your
For
judgment?
linear algebra.
Yeah,
So I think the course itself gives you an information, right? The course lists some reference books. Let me look into this.
because I just searched, I didn't get it.
The
Buy,
NPTEL course
Sir,
should,
I wanted
sir,
to
huh?
buy one book on linear algebra. Which author book, if I buy, will be good?
Rupesh sir,
Yeah.
what book has been prescribed? I have seen that one.
Which
Like
book?
it's very costly. It is 4,000 something. That one book.
I'll buy. Even if it is 5,000,
It
I'll
was
buy.
very
Don't worry.
costly.
Don't worry, I will buy. Tell me the author name.
No, no, I'm not telling to you. I'm telling to Rupesh sir that it's that book.
No,
So
if you
I
know the
think
author name, you tell me the author name, I'm telling.
I'm just posting the names here, right? You can just
Yeah, please,
look in the
please,
chat box.
please.
Let me show you. It's already present on the course page also, right? So these are few books. You can choose any one of them,
Which
right?
one?
And so I have pasted in the chat box. You can look into this. And the most popular one would be the Gilbert Strang's book. I think most of the Gilbert Strang has very nice lectures on YouTube for linear algebra. So
Gilbert
these are the Gilbert. So there is book number 4. I have posted in the chat box. You can see the book number 4. This is a very popular book if you want.
chat box. Is it? I'll just see. The chat box. Here, okay. Serial number 4, is it?
Yeah, book number 4. I have seen most of the people using this book. I have also gone through some chapters from this book.
Where is that? I'm not able to see. Chat box.
So you can always open up the course page also, right, and see it there. So first of all, no one has any doubts in the problems.
Gilbert, right? Gilbert, okay.
Gilbert Strang. Yeah.
Yeah, thanks a lot.
Okay. So anyone do you have any other doubts related to the concepts or the problems that we discussed today?
No, sir.
Okay. So let's end this session here. Thanks a lot, guys, and I will cover the remaining problems in the next lecture. Right.
Sir, last time on 15th August, your class was there. Actually,
Yeah,
I
yeah,
really don't want to miss any class. Like we have a nice interaction that we get a lot of opportunity to learn. So
yeah, yeah.
actually, I was not able to join. I've tried for half an hour, but I was not able to join on 15th August. I don't know what was the problem on that.
Okay.
So
So I don't think
last
there is any issue on the meeting,
And
Teams meeting side.
I've seen on the YouTube that classes had run on that day, but I
Hmm.
was not able to join. I don't know what was the problem because network issue was also not there. But I don't know, just like Microsoft, that part was coming. That it was written that hang on, just we are connecting, and nothing was showing. It took half an
So
hour, and still I was not able to connect on the 15th August.
So I think this was some network issue on your side, right? So first let
Okay.
me
Oh,
stop the recording. Yeah, right. Okay.
okay.
Uh, yeah. So there must